right now, the actual device you are using to listen to this deep dive, it relies on mathematics so ridiculously precise that it can predict the behavior of a single subatomic particle
Right.
to like more than 10 decimal places. It is, I mean, you could argue it's the most successful scientific framework in all of human
Oh,
history.
without a doubt, it's incredibly successful.
Yeah, but here's the wild part. If you ask the very physicists who actually wrote those equations what that math means, like what it says about the fundamental nature of reality, they will freely admit that they have absolutely no idea.
Not at all.
Or, even worse, they will just fiercely and bitterly argue about it. So our mission today is to unpack this glaring paradox right at the heart of quantum mechanics. Like, how can the world's most brilliant minds perfectly agree on the mind-boggling math of the subatomic realm, but then totally disagree on what those equations actually say about the universe we live in?
It is a massive epistemological crisis, honestly. And to visualize just how big this crisis is, our source material has this really brilliant framing device.
Okay, let's hear it.
So imagine two individuals standing side by side on a coastline, and they're watching the exact same sunset.
Right.
They both record the exact same physical data. The trajectory of the sun, the exact timing of its descent below the horizon, the shifting wavelengths of light.
So they agree on the facts.
Exactly. That shared objective data that represents the mathematics of quantum mechanics. The equations work flawlessly for both of them.
Yeah.
But then you ask those two observers to interpret the meaning of that data, and the consensus just completely shatters.
Like they see totally different things.
Yeah. One observer looks at the scattering light and constructs this beautiful poetic narrative about the passage of time and human mortality,
Sure.
while the other observer interprets the exact same scene strictly through the lens of orbital mechanics and atmospheric refraction.
I see. So the math is identical, but the realities they construct from it are completely irreconcilable.
Right. We've basically reached this frontier in physics where the data is so profoundly alien to our classical understanding that the numbers alone they cannot tell us what is actually happening behind the curtain of reality.
Okay, let's unpack this. Because for anyone listening who maybe leans toward pragmatism, I think the immediate reaction is usually, well, if the equations let us engineer semiconductors and MRI machines and quantum computers, why does the underlying philosophy even matter?
The classic shut up and calculate approach.
Yeah, exactly. Like, if the math works, why can't scientists just shut up and calculate?
Well, treating the universe like a black box, where
Yeah.
you just input variables and get these pristine predictions out without ever questioning the internal machinery, that's a perfectly valid approach if you're doing engineering.
Right.
But it is a terrible approach for fundamental physics. I mean, science advances through relentless interrogation of the unknown, not just by using mathematical tools.
You have to ask why.
Exactly. When physicists rely on equations they can't interpret, they're basically admitting a profound ignorance about the fundamental structure of existence. Historically, that obsessive drive to pry open the black box, to decipher the why and the how behind the what, that is the exact catalyst for all of our paradigm-shifting breakthroughs.
So to understand why this specific debate is so intense, we really have to go back to the origins, right? Back to the 1920s.
Oh yeah, the physics community was in a state of absolute panic back then.
Because of how bizarre the atomic world was behaving, they desperately needed an interpretation to make sense of the new math, which led to what we call the Copenhagen interpretation.
Right, Niels Bohr and Werner Heisenberg really championed this. It was a direct response to the Schrödinger equation. Erwin Schrödinger formulated this equation that described quantum particles not as, like, tiny, localized billiard balls.
Which is how we usually picture them.
Yeah, but instead he described them as waves, and specifically waves of probability. So according to the math, before a particle like an electron is actually measured, it does not occupy a single discrete location.
It's just sort of everywhere.
Basically, it exists as a superposition. It's a linear combination of all the possible states it could occupy, just distributed across space.
Okay, to ground that abstract math in a physical mechanism, let's look at the spinning coin analogy from the text. I think this really helps.
It's a great analogy.
So when you flick a coin onto a table, it spins rapidly. And while it is in motion, it isn't strictly heads and it isn't strictly tails.
Right, it's just a blur.
Yeah, that visual blur represents the mathematical superposition. It's this system in flux, containing the potential for multiple outcomes simultaneously. And it only resolves into a singular binary state when you literally slam your hand down, forcing it against the table.
And what's fascinating here is how the mathematics of Copenhagen actually handle that slam of the hand.
Oh,
Well, the equations describe the spinning coin, the wave function evolving smoothly and completely predictably over time.
okay.
But the very moment an observation occurs, Copenhagen dictates that this smooth mathematical evolution just abruptly stops. The wave function instantaneously collapses.
Wait, collapses?
Yeah, all those sprawling probabilities just vanish, snapping violently into one single localized point of physical reality. The act of measurement itself literally forces the universe to pick a definitive state.
See, that specific mechanism, the collapse, that is where this borders on mysticism for me rather than physics.
Oh, absolutely.
Because it implies that a physical property literally does not exist until it is observed. It places the observer, like, entirely outside the established laws of physics.
Right, like you're some kind of exception to the rule.
Yeah, like the observer is functioning as a cosmic referee who blows a whistle to force the universe into rendering a definitive reality. But does that mean reality doesn't actually exist until we look at it?
Well, that's exactly why this raises such a huge question about the fundamental nature of the observer. Copenhagen forces us to confront this framework, where human observation, or just interaction with macroscopic measuring devices, literally dictates the physical state of the microscopic world.
Which feels so wrong.
It does. It introduces this jarring, completely nonlinear jump into the math, which is otherwise so elegant. I mean, there is no equation explaining how or why the collapse happens.
It's just a rule they made up.
Basically. Yeah.
Yeah.
The postulate. It's just a rule awkwardly grafted onto the math by physicists to explain why we only ever see one outcome in our daily lives. Since we never observe a macroscopic object in a blur of superposition, Bohr and Heisenberg essentially just hard-coded a mathematical wall between the quantum realm and the classical realm.
Wow. Okay, so if you, listening right now, feel a deep intellectual resistance to the idea that the bedrock of reality is just a blurry casino game waiting for an observer to pull the lever, you are in very good company.
Very good company. Albert Einstein's company, to be
Yeah.
exact.
Right. Because Einstein was instrumental in building the foundations of quantum mechanics. He recognized the astonishing predictive power of the math, but he became its most formidable and relentless critic.
Yeah, Einstein's framework of the universe was built entirely on determinism and local realism. He firmly believed that objects possess definitive properties regardless of whether they are being observed.
As he famously said, the moon is there even when nobody looks at it.
Exactly. And furthermore, he believed that every single effect has a precise, traceable cause. So when Copenhagen asserted that at the deepest level, the universe operates on pure, uncaused randomness.
That the coin just randomly collapses to heads or tails without any physical mechanism dictating it.
Yes. When they claimed that, Einstein just flatly rejected it.
Hence his famous declaration, God does not play dice.
Right.
And that wasn't just some philosophical quip. He was essentially saying that if the math of quantum mechanics relied heavily on probability, then the mathematics were incomplete.
He felt something was missing.
Wait, so Einstein wasn't saying the math was wrong. He was basically saying the universe is hiding its homework.
That's a perfect way to put it. He argued that we were merely using probability as a crutch to mask our ignorance of deeper, undiscovered physical laws. So he theorized the existence of what he called hidden variables.
Hidden variables, what does that mean in practice?
Well, imagine watching a master illusionist perform a card trick. You might use probability to guess which card will be drawn, right?
Sure, like 1 in 52.
Exactly. But that probability only exists in your mind. It's born of your ignorance of the magician's sleight of hand. The physical mechanism of the trick is completely deterministic, you just can't see it.
Oh, I see.
Einstein insisted quantum mechanics was the exact same thing. He viewed the Copenhagen interpretation as this massive intellectual surrender. Like it was a premature declaration that the blurry wave of probability was the ultimate reality, rather than just admitting it was a temporary gap in human knowledge.
It's so funny. The historical irony here is that Einstein's absolute refusal to accept a theory built on inherent randomness actually drove the field forward more aggressively than the proponents of Copenhagen did.
Oh, completely.
By constantly designing these intricate thought experiments to expose the flaws and paradoxes of the collapse postulate, he forced experimental physicists to design incredibly rigorous tests. His stubborn refusal to settle for false certainty is exactly what laid the groundwork for entirely new branches of study.
Like quantum entanglement.
Exactly.
But the wild thing is, those rigorous tests eventually proved that Einstein's hidden variables do not exist.
Wait, really? So he was wrong?
Mathematically, yes. The randomness is real. The weirdness is inherent to the universe. But his core objection, that profound dissatisfaction with the arbitrary, completely unexplained nature of the wave function collapse that never faded.
Because it still doesn't make sense.
Right. Physicists remained deeply uncomfortable with a theory that required two totally different sets of rules. One rule for the smooth, wave-like quantum world, and another sudden, jarring rule for the definitive classical world of the observer. The field was absolutely primed for a radical reconceptualization.
Which brings us to Hugh Everett in 1957.
Yes.
Because if Einstein hated the idea of reality being a random coin toss and demanded we find the hidden mechanism controlling it, and Copenhagen demanded we blindly accept the randomness, Everett proposed a solution so conceptually extreme that it fundamentally altered the philosophy of science.
He really did.
Everett asked this radical question: what if the wave function never collapses? What if the coin mathematically lands on both heads and tails?
Yeah, to grasp the mechanics of Everett's proposal, we really have to look closely at the Schrödinger equation itself. As we
Just let the math play out.
Exactly. If the math says a particle exists in a superposition of multiple states, and there is absolutely no mathematical mechanism for a collapse, then every single state described by the equation must physically continue to exist.
Okay, here's where it gets really interesting, but also where human intuition just violently rebels. Let's use the analogy from the source text.
That's the road analogy.
Yes. Imagine reality as a road arriving at a fork. The Copenhagen interpretation states that reality travels down the road, reaches the fork, and instantaneously randomly deletes one path to travel down the other.
Right.
But Everett suggests that reality never makes a choice. The mathematics simply dictate that reality flows down both paths simultaneously. Every possible outcome continues somewhere.
And if we connect this to the bigger picture, we have to immediately address the obvious flaw in that concept.
Which is, why do we only ever perceive one path?
Exactly. Why do I only see a heads coin or a tails coin, but literally never both?
Right, because if both happen, shouldn't I see both?
Well, the answer lies in the mechanism of quantum entanglement and decoherence. Everett pointed out that the observer, you, me, the camera, the measuring equipment, we are also made of atoms.
We are part of the universe.
Yes, we are quantum systems too. So when you observe a particle in a superposition, you do not force it to collapse. Instead, your wave function becomes entangled with the particle's wave function.
So the observer gets pulled into the superposition?
Precisely. The universe essentially splits to accommodate the math. In one branch of reality, the coin lands on heads, and your wave function becomes entangled with the head state, registering that reality.
Okay.
But simultaneously, in an orthogonal branch of the universal wave function, the coin lands on tails, and another version of your wave function registers tails. The mathematical evolution continues unbroken, sprawling outward into infinite, mutually unobservable branches. This is the foundation of the many worlds interpretation.
Hold on, because a mathematically pristine equation does not mandate the physical existence of infinite doppelgangers.
It's a massive leap, I know.
If every quantum interaction, every tiny atomic fluctuation forces the universe to seamlessly fracture into countless branching realities, we are talking about a concept that is entirely untestable. If there is literally another version of me out there right now, but we have no telescopes capable of viewing adjacent realities, isn't this just sci-fi? I mean, without empirical verification, is this even physics?
Well, it is crucial to distinguish between a mathematical implication and an empirically verified fact. Theoretical physicists take many worlds seriously because of its austere elegance.
Because it requires no extra assumption.
Exactly. It requires zero additional postulates. It doesn't rely on mystical collapses or observers magically sitting outside the laws of physics. It just lets the universal wave function evolve naturally.
So it fixes the math problem.
It does. But, as the philosophical figure of the time traveler in our source material highlights, we must rigorously separate wonder from certainty. Many worlds is a breathtaking interpretation of the math, but it remains an interpretation. It is a philosophical lens applied to equations. It is not a proven, experimentally established map of the cosmos.
Which naturally pivots us from physics to neurobiology. Because whether reality operates through jarring collapses or infinite sprawling branches, both of these concepts give us a major existential headache.
Oh, they are intensely alien to how we experience life.
Right, so why do we struggle so profoundly with this? Why does the idea of a superposition or branching realities make our brains hurt so much?
To understand that, we have to analyze the evolutionary biological imperative of the human brain, The cerebral cortex did not evolve to solve differential equations. It didn't evolve to conceptualize subatomic states.
It evolved to keep us alive.
Precisely. It evolved to process macroscopic data, essential for immediate survival, tracking the trajectory of a predator, identifying the rigid boundaries of physical obstacles, understanding linear time so we can plant crops. The brain is fundamentally a predictive processing engine, and it is heavily optimized for classical physics.
So our brains are basically trying to force a messy quantum peg into a neat classical hole. We want a clean, single storyline, but the universe refuses to be neatly categorized. We filter out ambiguity because processing infinite probabilistic states is just metabolically devastating.
Yes, exactly. The human brain consumes a massive percentage of our body's energy, just rendering a single coherent stream of classical reality. Ambiguity in the ancestral environment equated to death. Certainty equated to survival.
That makes total sense.
Therefore, our neurological architecture aggressively enforces a paradigm of singular cause and effect. A rock is thrown, a tree is struck. We are hardwired to impose rigid, localized boundaries onto a universe that actually operates as a fluid, smeared wave of potentialities.
We are essentially demanding the universe conform to the limitations of our own cognitive bandwidth.
We absolutely are.
We want a clean storyline with a distinct beginning, middle, and end, because that is literally the only way we can process information without a complete cognitive collapse.
But the cosmos is under no obligation whatsoever to satisfy our cognitive preferences. The universe does not care that a singular timeline is comforting to a primate brain.
It's going to do what it's going to do.
Exactly. And learning to sit with that profound discomfort, to stare into the abyss of quantum ambiguity without immediately inventing a comforting narrative to close the loop, that is the ultimate foundation of scientific thinking.
It's the dividing line.
It is the razor-thin dividing line between clinging to dogmatic assumptions or inventing fantasies to fill our ignorance and genuinely exploring the mysteries supported by evidence, no matter how profoundly strange that truth turns out to be.
So what does this all mean? Like for you, listening right now, as you try to process the fact that the solid world around you might just be an illusion constructed by your brain to hide a branching multiverse or a collapsing wave of probability.
It's a lot to take in.
It is, but I think the takeaway is that science is an inherently unfinished story. Just as Einstein changed Newton's immutable laws of gravity, it is highly probable that future generations of physicists will write an entirely new chapter, one that might make both the Copenhagen collapse and the many worlds branches look completely outdated.
The pursuit never stagnates. In fact, our sources indicate that one of the biggest questions driving modern imagination isn't just debating whether the many worlds branches exist, but questioning whether they could ever interact.
Wait, really? Like one universe touching another?
Yeah, the concept of macroscopic quantum interference. Basically asking, could the barrier between these branching realities ever thin enough for one universe to mathematically influence another?
The implications of that are just staggering.
They are. Currently, it appears impossible due to the rapid rate of decoherence. But simply having the mathematical audacity to formulate the question pushes physics to the absolute bleeding edge of human comprehension.
It forces us to build better tools.
Exactly. It necessitates the invention of more sensitive instruments and the continuous, ruthless challenging of our most deeply held assumptions. Nobody knows the answer yet, but asking the question is what takes us there.
We began this deep dive by examining the comforting expectation of a shared objective reality. This whole belief that if we just possess flawless data, the meaning of that data must be universally self-evident.
And we've systematically dismantled that comfort.
Totally. The bedrock of our universe completely defies human narrative.
And I think that leaves us with a really haunting final question to mull over.
Let's hear it.
Well, if the greatest, most fiercely analytical minds in human history can examine the exact same mathematically flawless evidence and perceive fundamentally irreconcilable realities, what does that say about the rigid, uncompromising narratives you've constructed in your own life? If your brain is biologically engineered to force a singular, tidy narrative onto a messy, sprawling quantum universe, what if your deeply personal, subjective experience of time, of definitive choices and of missed opportunities is nothing more than a biological illusion?
These are tricks of the mind.
An illusion meticulously designed to keep you from being entirely overwhelmed by the infinite, staggering realities you are intersecting with